fire, when it fires or there is any firing happens, then somebody is writing something. I cannot see.
Sir, screen is not shared, sir.
Screen is not shared.
Yes, sir.
Yes,
And
sir. Screen not shareable. Now it's
Now
visible.
it is visible, sir.
no, then
Yes.
when I'm in the view
Now
mode,
it's
it's
visible.
now visible.
Yes, sir.
Yes.
Can you see? Now I change my slide.
Yeah, it is
No,
visible,
sir.
sir.
It's visible. It's visible, sir.
No. You just tell me whether my slides are changing or not when I'm changing.
No,
How do
sir.
you
Slides are not changing.
not changing? Okay, then actually this is one of the problem in Google Talk. So then I have to talk like this. Can you see now?
Sir, just you
Yes, sir.
move to next slide, sir. Yes, sir. It is visible, sir.
Now it's changing, but when I'm giving the full mode view, it's not working.
Sir, actually for that you have to share the entire screen. If you are sharing entire screen, in that case it will
Oh,
yes
okay.
sir,
I have just shared the screen. Okay. Okay, let's
window.
go like this. This
Okay
this
sir.
one you can see, right?
Yes sir, it is visible.
Okay. So here you can see these are the ore pyramidal cells. You can see these are the firing, and here there are two problems I'd like to highlight you here. First is just try to understand what is happening when the neurons are firing. It is, you know that the electricity always try to have it travel in the shortest path. So this is, you can see these are the different layers: pia matter, dura matter, arconode space, then skull, then scalp. Then on the top of the scalp we have hair, and here we put the EEG electrode. You can see here we put the EEG electrode, right? And then through this electrode, it's connected to some kind of amplifier, and then we get the signal. So there are many things are happening here. So what is our objective? Now, our objective is to get the good quality EEG signal. So the question comes, how can you get the good quality signal? Because see, always please remember, when you are working with a biosignal, always try to get the best quality data if possible. Because the biosignals are very tiny signal. Even among all the biosignal, EEG is the most difficult signal. Why it's difficult, I'll tell you later. But the question is, see, when the signal is arising from here, from the pyramidal cells, and when it travels through different paths, pia matter, dura matter, arconode space, then scalp, and finally we catch it here, definitely there is a chance of mixing of different kind of noises or different kind of other activity, right? That means your SNR, whatever you're going to get, might not be better or might not be good. So the question is, how you can get a very good SNR, good quality EEG signal, how you'll get it, right? So that's why you have to take many different kind of action so that you can get the good quality signal. So this is one challenge. As I told you, there are different layers are there, and electricity will flow from here to here. And also I told you, electricity, when it try to conduct, it always try to find out the shortest path. Let's say your electrodes which are sitting, you can see my cursor, which I'm placing on the screen. When you can see here, this is the electrode, EEG electrode. So EEG electrodes are, mostly on the surface of this our scalp. And let's say if the electricity is happening, the electrical activity is happening here, it may go straight or it may go an inclined path, depending on the shortest connected path. ये मान के चलो, let's say this electrode is on the top, straightforward top of this electrical activity, but there is some kind of problem where the electricity is not getting the complete path, that the circuit is open. Then what it will do? It will try to find out the other alternative path, right? So here, when you take the alternative path, then it would be very difficult to tell from where the signal has come. That's why the brain source localization is a very big problem. From the EEG, you must have heard about brain source localization. That means whatever the EEG data you are getting on the top of the surface, actually from which part it generally arises. This is the very big challenge, right? I'll explain you more later. Just keep in mind that why this is very difficult. So then question comes that how to measure the brain function, right? So there are different options. So definitely you need to cut the brain to measure the brain function. What we do different kind of imaging, and the imagings may be MRI, fMRI, DTI, NERS, EEG, MEG, many different techniques are there, right? But I'll talk about the EEG. This is what been assigned by your college, by the coordinator of this FDP program, that I should talk about the EEG, right? So EEG is first recorded by one German scientist, and his name is Hans Berger. That is also in 1902, and then first human EEG was recorded many years after this EEG. Okay, so you can see here. This is how it looks like. The setup look like. So this is the first time in the human EEG in 1920. It's been recorded. So it's a very huge devices, and you can see these are the paper traces, right? And now we are using different sets of different new kind of EEG system. And then this is the MEG setup. You can see here. This is a magnetoencephalogram. MEG is the brother technology of the EEG. You know that according to the Maxwell equation, electricity and magnetic field, they are perpendicular to each other, right? So where there is electric field, there is magnetic field. So here, in this kind of setup, three scientists, Edelsack, David Cohen, and James Jimerson, three people came up with this idea to measure the brain electrical field. But out of these three gentlemen, David Cohen, who joined in Pennsylvania University in USA, but when he came up with this kind of idea that he can measure the magnetic field of the brain, then the collegiate authority found him crazy guy. So they throw him out from this campus. And finally, MIT took this guy. And MIT provided him all the facility. And finally, these three gentlemen could develop this MEG setup. And that's why MIT got the first MEG machine in the world. And MEG has changed the way we record the brain signal, right? And now the device is not this much big, but it's a very small signal. And you'll surprised know that when they get this first MEG recording, they published this paper in 1972 in the Science magazine. Science is a top-notch magazine or top-notch journal in the world, right? So they published this kind of thing. And then these are the different kind of waves, in the EEG. So EEG signals are divided into different kind of frequency band. These are the nomenclature people use: delta, theta, alpha, beta, gamma, for our understanding. But again, many things depends on you, how you are taking the band of each frequencies, right, in the EEG signal. And all these frequency bands are related to some kind of functionality. Like delta people believe that it's related to the deep sleep, coma, or infancy. When you are having deep sleep, and if I'll record your brain waves, most probably I'll get the slow wave called the delta, and the range is 0 to 4 hertz. And if you are little bit sleepy, feeling sleepy, or in the childhood time or intelligence, it is represented by the theta. So delta is from 0 to 4 hertz, theta is from 4 to 8, then alpha is from 8 to 12, then comes beta, okay, then also gamma. Its gamma is not written here. So this is how the scientist is decided the band for the frequencies. But again, all these bands are made for our EEG understanding. But this is up to you how you are dividing the band. What I mean by this statement, I'll tell you later. And there is a rhythm called the mu rhythms. Mostly, those who work on the BCI, brain-computer interface, mostly the electrical motor activity is being recorded from the motor cortex at the frequency from 8 to 10 hertz, right? It's called the mu rhythms. And mostly in the BCI application, people use this kind of rhythms. So there are different kind of technology there. So it's very, very important to understand the technology. So, okay, I'm not going to the technology more. So most probably I'll talk more about the different kind of EEG placement system, right? So in this figure, you can see, I'll explain you in pen and paper again. Just see this figure. So this figure represents that how the different electrodes are organized or placed on the human brain. And this is called the 10-20 electrode placement system. So always we place the electrode by this 10-20 electrode placement system rule, because this is one kind of international convention people used to adopt. Otherwise, people will try to place their electrode according to their understanding, right? And this is not the good idea, because when you publish some kind of results, in order to understand it nicely, so I mean that's why the people have come up with the one standard electrode placement system, which is called the 10-20 electrode placement system. Okay, and using this system, you can see here how it looks like. So here I'm showing you a picture of one set. This is a 64 channel left side, and the right side is 256 channel. So even we usually put even 512 number of sensors. So it depends on your objective that and your fund available. Accordingly, you can go for the number of electrodes. But I believe if you have 64 channel electrode, this is a good number of electrode. You need not to go for 120 or 256 or 512 because you have many regions. So if you are planning to buy any kind of this kind of equipment, 64 is a good number, right? But if you understand this technology well, you know what to do and how to decide the best, the technology or the best equipment or the best placement according to your need, right? So now I'll go to the pen and paper, and if it's required, then I'll come back to the slides again. Okay. So let me connect to my another device so that I can show you in the pen and paper. Just allow me 3-4 minutes.
Sir, it is not audible, sir.
1 second. Can you hear me?
Yes, sir, you are audible.
Can you hear me?
Yes, sir.
Okay, it was muted. Okay, just tell me one thing. So what I ask you that please tell me if you have any doubt in EEG, so that accordingly I'll start. I mean, covering all your doubts also. Hello.
Yes, sir, you're audible.
Yeah, please tell me your doubt. I mean, what are the questions I need to cover um, in EEG?
Uh, Sir, if we want to know like some person is under depression,
Uh,
what patterns can be captured?
Patterns.
Patterns, yeah, which
Okay.
particular activity can be captured
Okay.
so that we can prevent suicidal cases.
Okay. Okay. Good. Any other questions? Any other questions you have? Anybody else?
Sir, can you tell us the relevant ECG, sir?
Relevant of?
Relevance with ECG, EEG and ECG.
Okay, EEG and ECG. ECG. Okay, let's say I'm writing neurological problems from ECG, from EEG. And any other questions?
Sir, I have one more question.
Yes, please.
Can we get fMRI data sets, sir?
Related to what?
Regarding these neurons activities only, to predict whether there is a sign of suicidal behavior or he is under depression.
Okay. Okay. Any other questions?
So, one question from my side. Actually, while acquiring EEG signal, how much it is important to lower the resistance? Means how much significant role it plays?
How much significant?
Significant role it plays, and what should be the means maximum value of resistance, so that below that we could get a good EEG signal.
Okay, you are talking about the during recording technique, right?
Yes, sir, related to EEG acquisition.
Okay, EEG equation. Okay. Hmm.
So
Okay.
few questions are also there in chat box.
No, I mean, I'm not looking at the chat box. Please tell me here. So please, I'm telling everybody, please don't write anything in chat box, because where I'm teaching, I don't look at the chat box. So you can tell me here.
So I'm reading this from Harjeet Singh. How can we see the EEG for human thinking process?
Okay.
And from Govind Swami, uh, Only one question, sir.
Um, okay. So let me just start from. Um, you can see my screen, right?
Yes, sir.
So what
Yes, sir.
happens? Okay. So I'm going to draw something. So mostly you have to understand the EEG instrumentation in a very better way. So definitely, okay, I'm just going to tell you very simple things. Not everything, I mean, because it will take some time. But what I can tell you, let's say this is your head, right? And this is ear. And let's say this is towards nose and this is the back side. So when we put some electrode, let's say these are my electrodes. You can see these are my electrodes, right? And as I told you, how we place the electrode? We place the electrode in 10-20 system. So let's say if this is my um, okay, this is node, okay, then this is mouth, whatever. So when we place the electrode, please remember, this is called Negian, N. This is called Inion. So you can touch the back part of your head and you can understand Negian and Inion, right? And this is a ear, this side here, then other side. So what we do, first, what we do, we try to measure from here to here 100%. From here to here 100%, right? And out of when you measure one from here to here 100%, how you will divide? So first you have to mark it after 10%. This is 10. Then again this is 20. Okay, and then again this is 20. Then again this is 20. This is again 20. This is 10. So 10, 20, 20, 20, 20, 10. Okay. Likewise, if will go from this side, this ear to the other side of the ear, then this is also 100%, right? So likewise, just like here you divided 10, 20, 20, here also you have to divide 10, then 20, then 20%, then you have to go to the other side, right? And then after that, what you will do, you have to rotate in this way, because your head is a sphere, right? So you have to rotate this way or that way. From ear, it will go towards the eye, and towards the eye, then again the other ear. Okay, this is again 100%, then the other way also 100%. So you have to again 10, 20, 20, 10, then 10, 20, 20, 10. Okay, this is called the 10-20 electrode placement system. So mostly what you will see, this line, the top line, and the line which will go from this ear to the other side of the ear, they will cross at a junction. This is called CZ. Okay, or you must have seen CZ. Z for, it's not written in book, but this is zenith. Okay, zenith means zero line. So basically, as you know that in the head is actually divided into two equal hemispheres. So if you look at your head from the top side, it will look like this. It will look like this. This is the top side from your head. This is the nose side, and this is nose, and this is a demarcation which separate left to right, left, and this is right, right, left hemisphere, right hemisphere. So this demarcation, whatever the electrodes will come, these are designated as Z. Whether this is CZ, you will first find out, I mean, whether FZ, CZ, OZ, all this, I mean, electrode Z means they are on the central line. Okay, OZ means if it's the occipital lobe, CZ means the central, which I'm telling you here, FZ in the frontal, right? So one more interesting thing, that whatever the electrode you will see, all these electrodes, I mean, the numbers are assigned like this. Numbers are assigned like this. Let's say this is my head, okay? This is nose, and let's say this is my hemisphere, left hemisphere, and this is right hemisphere. If any electrodes are there, let's say these are my electrodes, right? Let's say these are my electrodes. When I'm getting the signal from all this electrode, I'll give, I mean, people see any EEG setup, there is any number. Number means some number, let's say FP1, C1, right, C3, like this number you'll find. So C means central, F means frontal, right? You'll get F, you'll get P, you'll get O means occipital, P means parietal, okay, F means frontal, and the number denotes, let's say F1, P3, O4, the number denotes if this is a even number, even and odd, right? Even number denotes right side electrode, odd number denotes left side electrode. Clear? If you find any number denoted, I mean any region denoted by any odd number, then please take it as the left side. If it is even number, then right side. Okay. And after that, you know that this is the frontal. This is the frontal side, right? This is the occipital side. Okay. These are all frontal. This is central side. This is parietal side. This region, parietal. Okay, this is parietal side. This is occipital side. So this is only where you will, understand the physiology of the brain or the neuroanatomy. You can understand and how we place the electrode, right? So here, after you know that this is how you place the electrode, then comes some of the electronics. Let's say this is my head. This is my nose. This is my ear. Okay, and let's say this is my different electrode. Let's say this is one electrode. These are electrode, right? So either when you place this electrode, so when you collect the data, either you can go like this in this direction. I mean, basically in like this. You can go like this, or maybe you can go like array this one, this side, or you can go in this side. Okay, this is how we measure. So what does it mean? How will measure? Now these are all connected to some kind of amplifier, right? Amplifier means differential amplifier. You know that in the op-amp, basic circuit is one is, let's say this is positive, this is negative, this is output, right? Let's say I want to measure this one and this one. So what I'll do? I'll connect this one and then this one with minus. And what is the output I'll get? Let's say if something 4 is coming here, 2 is here, what I'll get? Now 4 minus 2, because it's a differential amplifier, I'll get 2, right? So this is one mode. Another mode, how people write, this is actually, see, this is, I'm using the 2 pole. This is called the bipolar recording. Bipolar recording, right? I can go for the unipolar also. Let's say here again, I'm connecting, for the unipolar, I'm connecting like this. Okay, and the negative terminal I sorted. Here also I'll get the output. Okay, so let's say here the same thing 4 is coming, it's a sorted, so I'll get 4 output. So in the top one, the bipolar I'm getting 2, whereas in the unipolar I'm getting 4. So you tell me here, in which mode generally you acquire when you acquire your signal? Please tell me how you acquire your signal. I'm asking all of you. I know that many of you are doing EEG kind of study, right? Can you hear me? Can you hear me or not? Please tell. I know that many of you are even, nowadays, almost everywhere I see they are interested in EEG or doing EEG. So, any one of you have recorded EEG signal until now or have some knowledge in this domain? No? अरे नहीं किया तो बताओ नहीं हमने किसी ने नहीं किया.
No sir, easy, just we have not gone into deep, but a little bit we have studied, sir.
Huh?
Little bit we have studied, sir, not in deep, sir.
Little bit
signals and all this related thing, I have not concentrated, sir.
No, you are not, but I know many people are attending to whom I know personally. They are already doing each kind of things, but nobody is telling here. So don't feel shy. Actually, I'm not going to tell wrong or right. I'm just asking you. No? Okay. Okay. So I know that you are not going to answer my question. Okay. Okay. So mostly out of this two kind of recording, what I'm telling you, whatever I'm telling you here, out of this two kind of recording, the interesting thing is that mostly in the hospital, I mean, if you go to any hospital for the collaboration, what you'll find, mostly they use bipolar recording. Okay, but unipolar recording is the best for research purpose. Unipolar. So whatever I'm telling, the first one, this is good for the doctor. This is good for the researcher. So the question comes, why? Why the previous one is good for doctor and the down one is good for the researcher, right? This is what I'm going to tell you. So let's say ये जो brain है ना, let's say this is a brain. Brain is not a very big thing, very small, right? Let's say one electrode is here, another is here, another is here. So my main objective is to record the brain signal, to record the neural activity. Okay. And as I told you, always my emphasis would be to increase the SNR, signal to noise. That means I need signal to be amplified, noise should be brought out, right? So how I can do this? Okay, let's see here in this condition. Let's see. I'm interested the signal over here in this electrode, right? Then what I can do? If I'll go to the bipolar mode, let's see what is happening. Let's say here I'll come to this bipolar recording close, and then I'll connect this one to my negative terminal. Let's say here my signal is S1 plus some noise N. Okay, let's say N1. Then in this area, my signal would be S2 plus N2. But as these 2 points are very close to each other, most probably the noises would be very much same, right? Why? Because noise is due to global noise or maybe electrical interference, and as these are very close, these are very much similar. So what will be the output? Output would be 1 plus N1 minus S2 minus N2. Then what will happen? S1 minus S2, okay, plus N1 minus N2. So as I told you, N1 and N2, the noise, whatever N1 N2, these are mostly the common source noise. I mean, if there is some noise over here and people see here, sorry, here both are same. So I can cancel N1 and N2. Oh. I can cancel both N1 and N2. That means this is almost 0. So what I'll get? I'll get S1 minus S2. And then, as I told you, my interest is to get the activity over here. What it can do? Because here you can see noise will completely cancel. Just only whatever the activity I can see in S2 would be subtracted from S1. And then I'll get the result here. But here what you'll find? Though you are getting able to get the good quality signal, but here the original signal is reduced by S2 because of this property, right? And now we'll see what is happening in the unipolar mode. In the unipolar mode, what is going to happen? Let's say this is brain again, and these are my electrodes. Let's say unipolar means, as I told you, my interest lies only with this electrode, right? Or this location. Then what I'll do? I'll connect with my amplifier. And as I told you, in unipolar mode, what I'll do? I'll sort this terminal. Then what I can get? Here the signal was S1 plus N1, right? But here you can notice that I have this noise, but at the same time, I am not losing anything in the S1. Whereas here I am losing some information in form of S2, because S2 I am substituting S1. That's why I am losing information here in the main signal. But here, though I am not losing anything, I am not losing anything. Only I am still have some kind of noise. But as you are expert in signal processing, you know how to handle this noise. And because your main job is not to throw out any amount of bit of your signal. That's why here my signal is always 100%. But as I had some noise, I can cancel out, or I can do some kind of signal processing, use some robust signal processing technique to remove this noise. While in the bipolar mode, as I'm not getting 100% signal. What I'm getting S1 minus S2, I might get 80%. So I'm losing some signal. But in the same time, I'm able to remove all the noise. So the question is, why the doctors use bipolar? Because doctors are not good in signal processing. They don't know, they don't have the knowledge how we can do the signal processing, but they do the visual analysis. ये देख के बताते हैं सिग्नल को, राइट? तो इसीलिए ये जो नॉइज ऑटोमेटिकली कैंसिल हो जाएगा. दिस इज अ गुड बेनिफिट फॉर देम, बट एट द सेम टाइम they are able to compromise with their signal. But the doctors, they mostly use EEG for to detect, let's say, if there are any spikes, the seizure or the epilepsy. For that kind of activity, this is a powerful method. But for many other cognitive processes, they will lose many information, right? But as I told you, if you are doing some kind of research to understand the brain function, go with unipolar mode of recording. In that way, you can preserve as much of information as possible in your signal. I hope this is clear to all of you. If you have any doubt, please ask me. Hello? अभी तक मैंने जितना पढ़ाया, whatever I explained to you, if you have any doubt, please ask me.
Devika Dev, do you have some question? You have raised hand. You can ask, sir.
Please. Yes. हाँ देविका, please go ahead.
आपने बताया
आपका वॉइस ब्रेक हो रहा है.
सर
Yes, please go ahead.
सर आपने जो बोला इसमें कि हॉस्पिटल में बायोपोलर यूज किया जाता है और रिसर्चर में यूनिपोलर, तो अच्छा समझ आ गया. मैंने फर्स्ट टाइम
I am telling not research. Actually, I am suggesting you to use unipolar for research. Even many places people use bipolar.
ये सर आपने वो क्लियर किया कि अगर रिसर्च में करना है तो किसी पर्टिकुलर पार्ट को अगर उसकी सिग्नल को लेकर के यूज किया जाए तो आपका 100% उसको यूज कर सकते हैं.
Yes.
सर मेरे लिए फर्स्ट टाइम है ये.
Okay, but you understood the concept, right?
Yes, sir. I understand this concept.
Very good. Very
Okay.
good.
Thank you, sir.
Any other questions? Okay, ये clear हो गया. Very good. Then now I'll tell you different thing. Okay. So now after getting all the signal, then whatever the signal you will get, let me draw some of the signal. Then okay. So then let's say from this EEG, how the EEG signal look like? Like this, right? Very random in nature. People see any signal, you look, it looks like a noise, right? So my first question to all of you, and this question will be with you for the entire session, for the FDP session, because there are many talks are there. So after attending all the talks, if you can answer this question to me, you can send me an email. Please send me the email to here, T Gandhi. My email ID is this, tgandhi@iitt.sc.in. What is my question? My question is like this. Let's say, ये जो signal, ये जो मैंने लिखा ना यहाँ, this signal, I'll give you this signal or whatever, I don't know. I am going to send you these two waveforms. These are my waveforms, right? And my question is, you have to tell me whether these are random noise or there is some electrical activity. How you will know that these are the signal from the brain or these are random noise? Got my question? You understood my question? इसका मतलब है
सर
हिंदी में
रिपीट
हाँ
हाँ सर रिपीट कीजिए एक बार
हाँ लेट्स से आपको किसी ने ये सिग्नल दे दिया, लेट्स से मैंने आपको दिया कि ये ले लो, ये एक ब्रेन सिग्नल है, राइट, एंड इसके अंदर बहुत कुछ इंफॉर्मेशन है, जैसे गोल्ड माइन, बट हाउ यू विल मेक श्योर कि दिस इज ए ब्रेन सिग्नल, नॉट ए रैंडम नॉइज? आई एम आस्किंग बेसिकली how will you differentiate between a brain signal? Brain signal means signal acquired from the brain, or maybe let's say how you will differentiate EEG from a random noise. Basically, I am asking whatever signal you are recording, how you will prove me that these signals are recorded from the human brain or these are reflection of the neural activity, not the random noise. I hope this is clear to all of you. Clear? I hope this question is clear to all of you, right? If you
सर
can answer,
क्वेश्चन इज नॉट क्लियर सर क्वेश्चन क्लियर नहीं है
clear नहीं है?
नहीं सर
Okay, मैंने आपको एक एप्पल और एक मैंगो दे दिया, राइट? मैं जैसे एक एप्पल लेके आपको पूछूंगा कि ये एप्पल नहीं है. If you think that this is apple, tell me how you know. If you think this is not apple, also tell me. Just like here, I'll give you this signal to you. I'll send you this signal. मान लो ये waveform है, इसीलिए मैंने लिखा waveform, right? These are all my waveform. Let's say this waveform आपको मैं दे दूंगा, and आपको पूछूंगा ये बताइए ये whether is a EEG or random noise. समझ में आया?
जी सर
हाँ, whether it's a EEG or random noise, you have to tell this.
ओके सर
Okay, very good. Okay, so now there are, you know that this is the thing. So okay, let me share one slide with you. Where it is? Slide is. Just 1 second. Yes. Can you see my slide? Understanding concepts and processing of EEG evidence. Can you see? Can you see my screen?
Yeah, it's visible, sir.
Okay, very good. So here, okay, I'm bringing this slide. So this is very interesting, you can see. Okay, in this slide you can see. So here the signal is of two types, mostly determined and stochastics, right? And again, the determined are again divided into different kinds: periodic, quasi-periodic, transient. And stochastics are again two types: stationary, non-stationary, right? So periodic, what do you mean by periodic? If signal is repeating after a constant time interval, you know, sine wave or cosine wave we call periodic. ECG is called the quasi-periodic, right? And then transient signal. Transient is basically, this is a spike kind of thing. Then comes stationary and non-stationary. So you can see here, EEG signal is a completely non-stationary nature. Non-stationary means the signal property does not change with time. Okay? Whereas in stationary, the signal property here, stationary, the signal property does not change in time, and non-stationary when the signal property changes with respect to time, right? So that's why when we apply some kind of technique, we first need to convert the EEG signal to the stationary format, and then we can apply different techniques. So as I was telling you, many people, 90% people work in this domain, they do the biggest mistake here. Without converting this non-stationary signal to the stationary format, they apply different kind of techniques and then they publish the paper. There they do the mistake, big mistake, right? So what does it mean? What do you mean by this stationarity? Okay, already I have shown you this picture. Okay, already explained to you what do you mean by this 10-20 electrode placement system. and then let me come to this kind of signal. So this is a very important property of the signal. Okay, so let me in the same time get my okay, here. So let's say if I am giving you this signal, let's say this is my one waveform, right? This is my waveform. ठीक है, ये मान के चलो this is a completely sinusoidal wave, okay, or periodic wave, completely periodic in nature, though I could not draw it properly, but just imagine that's a periodic in nature. Let me put axis. Okay, so you know this is how we calculate a cycle. This is one cycle from here to here, right? This is one cycle. Then another cycle starts from here to here, okay, and from here to here, let's say one cycle. Let's say if I'll give a timeline here, okay, let's say up to this time, from this time to this time, this is 3 seconds, right? Okay, just see here. So I know this concept is not, I mean, when I ask this very simple question to student, or maybe when I used to go to take an interview, even people cannot explain this. You know, sampling rate is one of the most important component of signal processing. Sampling rate means you might be knowing this thing, sampling rate, right? That means number of samples per second. Number of samples per second. Sampling rate, that means sampling frequency. Fs, what do you mean Fs? The number of cycles per second, right? If I'll ask you, what is the frequency of this signal, what would be your answer? Please tell me. Let's say this is 3 seconds. So what is the frequency of the signal? Please tell me. If somebody can tell, I have already given the clue. Please tell me what is the frequency of the signal. The sine wave which I have drawn, what is the frequency of the sine wave? Please tell.
1.
1. Okay. Any other answer? 1. So I got one answer, 1. Any other answer?
2 pi by 3, sir.
Huh?
2 pi by 3.
2 pi by 3. Okay. Any other answer?
So 1 by 3 hertz.
1 by 3 hertz. Okay. Any other answer? See, I'm not asking any big question. Because I don't know any big things. I only know small things. That's why I'm asking small things to all of you. I know after my talk, all the speaker will tell you very big things, even which I believe that I cannot understand. But I'm just going to ask you only simple thing, tiny things, and you have to tell.
Sir, it is 1. I think it is 1. 1 sample per second.
1. Your answer is 1. 1. Okay. So my question is, what is the sampling frequency of this sinusoidal wave which I have drawn on the screen? I have already written everything. Just you have to look at and tell. Huh? No answer? Okay. Okay, no problem. See, I have already written here, sampling frequency is equal to number of cycles per second. Means how many cycles per 1 second, right? So, though 2 of you have given the right answer, but again the answer is not right, again wrong. Why? Because you didn't tell the unit, right? 1, don't tell like 1. What do you mean 1? 1 kilohertz, 1 hertz, 1 kg, 1 kilometer. What do you mean by this? This is 1 hertz, right?
Yes, sir, 1 hertz.
So please tell the complete answer. So
Right, sir.
when the sampling rate is number of samples per second or number of cycles per second, that means you have to see how many cycles. This is I told you, sorry. This is I told you. This is what I told you, that this is I told you. This is one cycle. First one cycle, then again one cycle, 2 cycle हो गया, then again 3 cycle. तो ये 3 cycle complete करने के लिए कितना टाइम लगा? Already I have written 3 second. इसका मतलब है sampling frequency is equal to 3 cycle by 3 second. That means 1 hertz. Very clear, simple, right? So this is called the 1 hertz. So my next question is, what do you mean by signal processing? ये बताओ, signal processing का मतलब क्या है? What do you mean by signal processing? जल्दी जल्दी, नहीं तो टाइम खत्म हो जाएगा. Even actually, truly speaking, I don't like teaching in this online kind of things, and even I cannot take, even at IIT also I cannot take more than 1 hour lecture, because when I don't see the participants or my student in front of me, I don't get the feel. So that's why I'll continue until 4:30. Okay, so please, if you'll fast, then I can talk to you fast. What do you mean by signal processing?
Sir, capturing the data from the signal and transforming it into, like after processing, transforming it into certain piece of information.
Okay, ये मुझे बताइए. Let's say you will go to your village. Maybe I don't know whether you are from village or a city.
Yes, sir.
Let's say, okay, maybe in your city also, you go to a sabji wala. Okay, let's say maybe you know some sabji wala, and the sabji wala also knows you that you are a great scientist or you are very good in signal processing and all this stuff. तो उन्होंने किससे सुना ये सिग्नल प्रोसेसिंग वर्ड किससे सुना, और उन्होंने आपको पूछेंगे कि आप बताइए सिग्नल प्रोसेसिंग का मतलब क्या है, ये इसका मतलब क्या है. व्हाट यू विल टेल हिम?
सर टू एक्सट्रैक्ट इंफॉर्मेशन एक्सट्रैक्ट करना सिग्नल वेवफॉर्म से.
ओके,
सिग्नल से.
ओके, ये बताओ उनको कैसे, किस लैंग्वेज में बात करेंगे उनको समझ में आएगा. दिस इज व्हाट आई कैन अंडरस्टैंड.
वह एक तरह का तरंग है.
हाँ, एक तरह करंट है.
वह एक तरह वेव है, एक तरह का, मतलब बस ऐसा ही है.
वेरी डिफिकल्ट क्वेश्चन मैंने पूछ लिया ना.
Sir, converting into an information which is understandable for the other person, or maybe the person or the device who is on the other end.
Okay, madam, you are from which city?
I'm from Delhi, sir.
You are from Delhi.
Yeah.
कौन सी जगह से आप हैं?
Sir, University of Delhi.
ठीक है, मैं आपके कॉलेज का आता हूँ, हम चलेंगे सब्जी वाला को ये वाला डेफिनेशन बताएंगे, एंड इफ यू विल अंडरस्टैंड मैं आपको बहुत बड़ा वाला पार्टी देने वाला हूँ. डू यू थिंक दैट ही कैन अंडरस्टैंड? हेलो, ही विल नॉट, राइट? तो ओके, सिग्नल प्रोसेसिंग का मतलब ये देखिए, वन थिंग आई वुड लाइक टू टेल टू ऑल ऑफ यू, हमारा लाइफ बहुत सिंपल है. जितना भी आपकी चार तरफ प्रॉब्लम है ना, जितना भी इंजीनियरिंग प्रॉब्लम्स है, दीज आर ऑल वेरी सिंपल. तो हम क्या करते हैं ना, उसको कॉम्प्लिकेटेड बना देते हैं, एंड कॉम्प्लिकेटेड वे में हम उसको देखना शुरू करते हैं, इसीलिए हमें बहुत ज़्यादा कॉम्प्लिकेटेड लगता है. बट ट्रूली ऑल दिस प्रॉब्लम्स आर वेरी वेरी सिंपल इन नेचर. एंड प्लीज जस्ट, आई मीन, बिलीव मी, if you will try to answer these questions in a very simplistic way, I'm telling you, you can get big papers like Nature, like PNS, like big paper. I mean, which are even you cannot compare. I mean, people get one Nature paper, it's equivalent to even more than 100 IEEE transactions, right? So this is what I'm telling you. So all the big thing happens in a very simplistic way. सिंपल चीज है. सिग्नल प्रोसेसिंग का मतलब ये है, सिग्नल का मतलब एक वेवफॉर्म है, राइट? जैसे मैं बात कर रहा हूँ, व्हेन आई एम टॉकिंग टू यू, दिस मींस ये सिग्नल भी हो सकता है, नॉइज भी हो सकता है. लेट्स से व्हेन आई एम टॉकिंग अबाउट सिग्नल प्रोसेसिंग और ब्रेन और मे बी योर, दिस इज योर इंटरेस्ट, दिस इज ए सिग्नल फॉर यू. बट इफ आई टॉक दिस थिंग टू ए लेमैन, दिस इज ए कंप्लीट नॉइज फॉर हिम, बिकॉज he will not get any information from my talk, right? So ये जो वेवफॉर्म है उसको समझना, उसके बारे में बताना सिंपल वे में, उसको समझना उसमें है क्या, ये जो एक तरंग है, ये तरंग में क्या छुपा हुआ है, उसको समझना ही हम उसको सिग्नल प्रोसेसिंग कहते हैं। कैसे? तो इसीलिए whatever the signal you will get, let's say I'll draw like this, right? Or maybe I'll give some time kind of information कि this is varying plus minus 5 volt, and I'll give some information, let's say 1 second, and मैं वो तो पूछूंगा ये है क्या, then you can tell maybe it looks like a sinusoidal wave, और इसका peak वेरी हो रहा है प्लस माइनस 5 वोल्ट, एंड दिस इज प्रेजेंट फॉर t इक्वल टू 1 सेकेंड, ये 1 सेकेंड तक है, यू विल टेल लाइक दिस, ओके, एंड दिस इज व्हाट वी कॉल द विजुअल एनालिसिस. That's why in signal processing we process the signal in 3 different ways. First is what? First is you just try to see, this is called the time domain. Time domain, you must have heard time domain. Second is called the frequency domain. Third is called the time frequency domain. You must have heard this terminology, right? Frequency domain. And this time frequency domain, you will get n numbers of technique. S transform, wavelet transform, Q transform. ऐसे कोई ट्रांसफॉर्म नहीं है जो नहीं है दुनिया में, राइट? यू विल गेट मेनी डिफरेंट काइंड ऑफ थिंग्स. व्हाई? देखो ये जो टेक्निक्स है, ये टेक्निक दीज आर ऑल मैथमेटिकल टूल, मैथमेटिकल टूल्स. ये जो आपने आजकल सुना होगा मशीन लर्निंग टेक्निक्स, ये कुछ नहीं है यार, ये सारे वही साइंटिस्ट ना, हम क्या करते हैं ना, ये सारे सेम चीज को डिफरेंट वे में पुट करके कहते हैं ये देखो नया चीज हम लेके आ गया. ये जो आर्टिफिशियल इंटेलिजेंस आप सुन रहे हैं आजकल, दीज आर ऑल आई मीन आई डोंट सी एनी difference between signal processing or pattern recognition. The same thing, just we are making it a very big deal, right? So that's why my advice to all of you is try to understand all these basic fundamental things. If you can understand, you can easily do the signal processing, machine learning, artificial intelligence, everything you can do, right? So a time domain analysis में क्या है? Time domain means with respect to time, when the samples are there, how we are trying to understand, right? If it's a periodic, then, or if there is some information there, we can most probably tell something about it. But if the signal is not periodic, we cannot tell anything about it, right? Let's say जैसे ये मैंने अभी एक frequency दिखाया. Let's say again I'll draw another signal. ये मान के चलो ये एक sinusoidal wave है, right? And let's say 1 second. मैं आपको पूछूंगा टेल मी व्हाट इज द व्हाट यू सी इन द सिग्नल, और टेल मी इस सिग्नल के बारे में. तो इफ इट्स अ साइनसॉइडल एंड यू नो द टाइम पीरियड, देन यू कैन टेल, और लेट्स से यू नो द वोल्टेज रेंज, लेट्स से 10 वोल्ट प्लस माइनस 10, देन यू कैन टेल दैट दिस इज 10, आई मीन दिस सिग्नल इज लुक्स साइनसॉइडल, इट्स वेरीज फ्रॉम -10 टू +10, एंड इसका फ्रीक्वेंसी कितना है, यू कैन काउंट लाइक दिस. If it's let's say 10 hertz, you can easily count it. But if let's say it's 50 hertz, then it would be a little bit difficult, but still you can count. But you know that whatever will come on your way, you never know what would be the frequency. Let me show you some other very interesting signal. Here you can see the top one looks very simple, right? It looks a sinusoidal. Second one is sinusoidal. Third is sinusoidal. But here, very interesting thing is that if I'll ask you to tell me what is the sampling frequency or what is the frequency of the signal, you can easily tell. Top one you can easily tell. Even the second one also you can tell. But third one, though you can tell, but it will take a little bit of time because it's very tiny one, right? So when you cannot count the frequency in this way, what we'll do? We apply the Fourier transform, FFT kind of things, right? And then it will give you the Fourier. You can see here, this is the Fourier transform, FFT. Okay, you can see the third signal, this signal, when we don't know what is the frequency. If you apply the first Fourier transform, what you can get? You will get a spike over here at 50 hertz, right? You can see here. So my question is here, when some of the information you cannot see by naked eye or it's very difficult, then you can apply the FFT. But in first Fourier transform, only it will tell you about the frequency component, which are the frequency component present in the signal, right? Here, if I'll show you the signal, and if I'll ask you, tell me about the signal, can you tell what is the signal is about? Or can you tell something about the signal? Or whatever you can tell, please tell. Let's say मैंने आपको ये सिग्नल दे दिया, इतना ही इंफॉर्मेशन, मैं आपको बताऊंगा कि ये सिग्नल प्रोसेसिंग जो आपका नॉलेज है इससे बताइए है क्या. What is this?
Stationary signal.
ये स्टेशनरी सिग्नल आपने देख लिया ना नीचे. हाँ, I know it's
No,
written.
no time variation, just sticking on to same pattern.
Okay. And any other things, other information you can tell about the signal?
The mean of the signal is 0, no, sir?
I don't know.
Periodic signal?
Does it look like a periodic signal, madam? उसका period कहाँ से कहाँ आप calculate करेंगे? तो looks like a random signal. How it's a periodic signal?
Non-periodic.
Yeah, non-periodic.
Okay. Definitely, it does not look like a sinusoidal signal. Maybe it may be a combination of many sinusoidal signal, but not a. I mean, it does not look like a simple sinusoidal signal, right? तो ये सिग्नल को देख के आप ये बता सकते हैं कि looks like a very random kind of signal. इसका टाइम है maybe up to 500 millisecond and इसका amplitude है -3 to +3. इतना ही उसके ऊपर आप बोल सकते हैं. यही सिग्नल प्रोसेसिंग है. सिग्नल प्रोसेसिंग और बहुत कुछ बड़ा वाला बात चीज नहीं है. There is no bigger than this. यही सिग्नल, यही जो मैं देख के बताया, यही है सिग्नल प्रोसेसिंग, राइट? फिर क्या कर सकते हैं इसको? लेट्स से ये मुझे समझ में नहीं आ रहा है कि इसका फ्रीक्वेंसी क्या है. देन व्हाट आई विल डू, मे बी आई कैन अप्लाई द फास्ट फॉरियर. ठीक है, जो मैथमेटिकल टूल है फॉरियर ट्रांसफॉर्म. प्लीज म्यूट योरसेल्फ. हाँ, सो मे बी इफ आई अप्लाई द फास्ट फॉरियर ट्रांसफॉर्म, आई माइट सी some kind of frequency information कि if something present. Okay. तो ये जो सिग्नल था, ये क्या क्या सिग्नल था ये देख लो यहाँ. दिस इज ए मिक्सचर ऑफ 4 cosine wave. Cosine is also, you know, is one kind of sinusoidal signal. I mean, it's a cosine signal, right? So first one is cos 2 pi ft. Second is red color are my frequency. Red color, you can see f1, f2, f3, f4. So the first one is 10 hertz, then 25 hertz, then 50 hertz, and 100 hertz. So what I did, I combined all these 4 sinusoidal waves or cosine wave and get another complete signal which is called the xt. And which is the xt? This is the xt signal, right? But यही xt signal के अंदर ये सारा frequency है. So you can imagine when I'm mixing these 4 individual sinusoidal wave and I'm getting something else which does not look like a sinusoidal, and the question is how I can get this information. So as I told you, if you apply this fast Fourier, you can easily see this frequency. You can see what I've written: 10, 25, 50, and 100. These are the frequency component coming here. 10, 25, 50, 100. 10, 25, 50, and this is a 100. Okay. So this is a very interesting crux here. Please, actually, I'm telling you very simple stuff about signal processing. If you understand this basic concept, you can do wonders in this domain, right? Okay. This is a signal. Tell me about the signal. Tell me about the signal.
Sir, FM frequency modulated signal, it might be.
हाँ, ऐसे लग रहा है. ये जो हम frequency modulation, amplitude modulation की बात करते हैं, ये frequency modulation kind of, right? Okay. Any other information? क्या है? Simply जैसे मैंने ऊपर वाला बताया, ये भी सिग्नल देखे तुम यही बताओगे कि looks like a chirp signal. इसका frequency धीरे-धीरे बढ़ रहा है and it ranges from 0 to 1000 millisecond and इसका amplitude है +2 -1. इतना ही बता सकते हो. But you cannot tell इसमें क्या frequency component present है, right? Then what I'll do? I'll apply again the FFT. Again, this is a similar kind of signal. Okay. So if I'll apply the FFT, here you can see. Okay. Again, here also this is the same signal. I mean, same signal in the sense, same sinusoidal signal having same kind of component: 10 hertz, 25 hertz, 50 hertz, 100 hertz, right? But see how they look different. Same signal. Again, I'm going to the, okay, let's just hold on. See, can you see these two waveform? Can you see these two waveform? हेलो, कैन यू
Yes,
सी
sir.
दिस? ओके,
Yes, sir.
ये दोनों जो वेवफॉर्म है ना, इसमें यही 4 कंपोनेंट है, 10 हर्ट्ज, 25 हर्ट्ज, 50 हर्ट्ज, 100 हर्ट्ज, राइट? यही 4 कंपोनेंट का दोनों वेव है, बट सी हाउ दे लुक डिफरेंट. ओके, you can see here the left one is starting with higher frequency and going towards the lower frequency, but the right one you cannot see any frequency, it's a mixture. The left one is called non-stationary signal because here the statistical property is changing after certain interval time, or the right plot is called the stationary signal because here all the frequency component present at all time. Let me write in a Word document so that you can understand clearly. Please look at my equation. Let's say I took, in that example, I took cos 2 pi f1t plus, see, there are two kind of variable I'm using here. Okay, t1. Let me take t1. Cos 2 pi, okay, f2t, t2, let's say 2 wave I'm taking, okay, and let's say this is a nahi, this is another wave called x. So here one more term I can introduce. I can introduce also one term called amplitude. Let's say this is y1, this is y2, okay. So first thing what I did, this is my frequency component here. I took, let's say, 10 hertz and this is 25 hertz. If I'll plot these two signal, let's say this is a signal like this and this is also a signal like this, right? And when I'll mix these two signal, it will look like this, right? This is one case. Here another terminology I've written, T1. Let's say here T1 and T2 are all same, T, both are same T. That means for all the time T, for all time, this signal with frequency 10 hertz and 25 hertz are present, right? But if I'll change this equation like this, see, I'm not going to change in a big way, a little one, the same x I've written, same y1 cos 2 pi f1 t1, okay, plus cos y2 cos 2 pi f2 t2. So f1 f2 I'm just replacing with 10 and 25. t1 को मैं क्या किया, पहले ले से 0 to 5 सेकंड तक t1 है, फिर t2 कितना है ना 5 to 10 सेकंड. यही t1 t2 I just varied, and this signal would be completely non-stationary in nature. That means initially I might get slow wave like this, after 5 seconds तक, then मेरा frequency थोड़ा increase हो जाए क्योंकि I'm increasing to 25 hertz, right? ये ले हो गया 10 to 5 hertz, ये 5 second, and ये 5 second to हो गया 10 second, and this is called non-stationary because if I consider the signal at a time, then it is vary from, I mean, low to high with different time interval. That's why it's called the non-stationary signal. Okay, so you can see here, this is what I was talking about here. Here, the same signal, okay, people see the equation here. Here you can see here T is same. For all time, different frequency component present. That's why it's called the, you will get all, I mean, statistical property is not changing from time to time. But here, the statistical property is changing from left to right. Okay. But here, interesting thing is that if you will do the power frequency spectrum, again, there are two very, very interesting differences here. So here, in the right case, this is the power spectrum. And here, you can see the spikes are same, equal in length. But here, the spikes are different length, right? Again, one more thing, if you look at the, near the zero baseline, there is some sharp, I mean, the sharpness is here in the right hand picture, for some jerky moment in the left hand picture. So this is actually this is the beauty of signal processing. This is what we do, right? So from this kind of analysis, you can easily tell that maybe in the right hand picture, as all frequency components are present at all time, that's why you don't see any jerky nature. And as all frequency components are present at all time, that means all frequency components are contributing the equal amount of information. That's why the height are same. Here in the left picture, you see the heights are not same because all frequency components are not present at equal time. So here 50 Hz and 100 Hz, they present for bigger time, and the 10 Hz and 25 Hz, they present less amount of time. This is what it says, right? And the jerky moment, you can see left side picture, a jerky moment because the frequency is changing after certain interval of time. Or in the right hand picture, if the frequency does not change, that's why it looks very smooth. And this is what we call the signal processing, right? So when you want to know that at what time all these frequency components are changing, then you have to go for the time frequency representation, which we call the wavelet decomposition, wavelet, right? So in the wavelet, you know that always we try to handshake between the frequency as well as time information. And I'll tell you, those who are new to wavelet, please study any tutorial by Ravi Palekar. There are many interesting tutorials there by Ravi Palekar. When I was a student, I used to study, I mean, I'm talking about 15-20 years back. I used to study his tutorial. I mean, you will Google, this is a picture from the tutorial of Ravi Palekar, right? So in this way, you can, I mean, in the wavelet, we apply some kind of mother wavelet, and then we try to handshake between time resolution and frequency resolution, and then we can tell that this frequency component exists at this time interval, right? But as you know that according to the Heisenberg's uncertainty principle, time and momentum and position you cannot measure. Likewise, here also, you cannot measure precisely the time and frequency information. You have to handshake, right, with all this information. So also, I mean, with this EEG signal, okay, what you can do, you can also apply different kind of machine learning technique. I'm just looking at the graph. If I have some machine learning graph here, okay. Yeah. So what you can do, whatever the signals you are getting, if you want to get some unbiased kind of results, what you can do, you can train. I mean, if you are going for the supervised kind of classification, you can train with some set of information data and then test with some other set of information data. But also you can do the unsupervised way of experimentation, and in that way you can find out which are the most informative sensors, right? So using this kind of knowledge, using this kind of fundamental knowledge, you can do very high quality research in your domain. I mean, if you are interested in this domain, right? And definitely, I know that this 1.5 hours is not enough to understand more about this EEG kind of things. See, I mean, the first thing is that again and again I'm telling you that please try to understand the fundamentals. When you are going to work on the biomedical signal, you need to understand how this mechanism is happening, or what is the correlate, neural correlates, or the fundamentals behind it. And in the same time, you need to have a little bit of good background in mathematics to understand the signal processing. And if you have these two good expertise you can combine and you can answer many big questions of the science, right? This is from my side. And going back to your questions, you asked that how EEG and ECG are related. Definitely, ECG and EEG are related in that way that brain is the master controller of anything, right? And brain control, even your heart rate, everything. So that's why we divide the nervous system into two parts, peripheral and central, right? So central nervous system, you can see the green color on the brain and spinal cord, and peripheral nervous systems are connected to different organs of our body. So whatever you are doing, accordingly, it will be reflected by your ECG signal. So that's why in biomedical signal processing, we apply some kind of multimodal approach to answer any questions, right? Then second question was, can we diagnose suicidal behavior or depression from the EEG signal? Yes, you can do it. Depends on your expertise in understanding the signal. And if you have good signal of this person, then definitely you can understand. Third is, how from where you will get this fMRI data. fMRI data, you have to have a collaboration with some medical institute or any imaging institute, and then depending on your protocols, Or let's say if I'm interested to do any clinical data, let's say in the COVID, in COVID time, many people are working the COVID data. So if you will approach any kind of clinics or hospital to get some CT scan also you can get. But in my lab, mostly in my lab, we do many, basically all real-time experimentation. We have the access to this imaging center. So my student need to go to the imaging center and they get thousands of volumes of images for different kind of experimental paradigm, and then we analyze. So in that way, you can get the MRI or MRI data. Then you ask, okay, during the recording techniques, what would be the impedance? So please, when you put the electrode, you always need to try to reduce the impedance, because when the impedance or resistance is less, your conductivity would be more. So this is the simple idea. In electrical engineering, we've studied, we know that in order to have the good conductivity, we need to reduce the resistance. This is what you have to do. In the EEG, that's why we put some kind of electrode gel so that it helps us in reducing the electrode impedance. And this electrode impedance varies from person to person. Somebody has 10 kilo ohm, somebody 20 kilo ohm. So that's why if you are doing the electrode, some people say that, oh, the impedance should be below 10 or 10 kilo ohm. But please mind it, everybody has their own impedance. My head is different from your head. So you have to take your own judicious decision when you are recording the signal. Okay. So then last question was, how can you see EEG from human thinking process? Definitely, when your thinking process is changing, definitely the brain signal is doing all this job. So it's a tiny activity. So it's up to your skill, how better you can visualize it. So people are now already, trying to do all this kind of things, how to decode the human brain. You can do it, but depends on your understanding and your expertise. Thank you very much. And if you have any questions, I'll be happy to answer your question.
Any other questions, participants?
Sir, please mention the name of the person which you told about for wavelet transform.
Oh, Ravi Palikar. If you type in the Google, Ravi Palikar is...
Sir, what is the spelling?
Ravi Palikar, एक second. Wavelet, I'm also Googling it.
Yeah.
Wavelet tutor by Palikar. Palikar, P-O-L-I-K-A-R.
And R-A-V-I.
R-O-B-I. Ravi, R-O-B-I. Palikar, P-O-L-I-K-A-R. Ravi Palikar. He's from Rowan University. So you can actually, you'll get many materials, but when I was a student, I used to study his tutorial, and it's very, very easy to understand.
Any further queries?
Okay, so there are no queries. I would like to thank Tapan sir. Myself and Dr. Mridu both attended one of his recent workshops, and then only we thought that whenever we organize workshop, we'll call sir. We spent much more time with sir last time. It was around 10 days workshop which we attended. So thank you very much, sir, for giving your time. I know that you are very busy, and still you were able to give your time and share your knowledge. Thank you very much, sir.
Yeah, so actually, for everybody, every year during March, I organize this big workshop on this brain mapping and artificial intelligence. So always please check my website. If anybody is interested, you can join in that workshop. So, and definitely, during this short time, it's very difficult to tell everything. But always, last 2 years, due to this COVID, we are having this online workshop. But once this COVID problem settle, then most probably we'll again convert in the offline mode, because understanding all this thing, it requires the offline kind of training, right? And online is challenging, a little bit of challenging. Yeah.
Yes, I strongly recommend you all to attend that workshop. Thank you very much, sir. If anybody wants to ask something else, they can. Otherwise, we'll end the session. I think we have half hour. So if you all agree, we can have one half-an-hour session from my side. Few things which were pending.
So can I leave?
Yeah.
Yes.
Thank you very much, sir.
Okay,
you can
no
leave,
problem.
sir. Thank you. Yes, sir.